We were counting this out and he wants to count it. And Connor was he's nice. Really?
So, are there any makeup labs on Saturday? Oh, no?
I'll post the rules of the lab later.
Online?
Give me some, yeah.
Sorry guys.
None of them are.
No, I mean,
Okay, are there any questions before we get started? I guess in the last lecture, Professor Juan Alvarez came and talked about linearity and superposition. I suppose you know about that now. Are there any questions on this linearity and superposition methods? If not, let's move on to Thevenin and Norton equivalence of resistor network, if there are no questions on this. But let me tell you the key summary of this. That is that if you have a very complicated network, that you have maybe a current source 1 plus maybe a current source 2, and then maybe a voltage source somewhere, and another voltage source 2, plus many other ones, and they are connected in a very complicated fashion. The key thing is that if you want to look for any solution anywhere, be anywhere inside the circuit, that this voltage that you measure or try to extract somewhere inside this circuit has to be a linear superposition of all these sources. You can say it's K1 Vs1 plus K2 Vs2, and you can go on and on with as many voltage sources as you want, and then plus the current sources. It may be, let me see, a good number would be R1 Vs1 plus R2 Vs2. Sorry, IS1. Okay, IS2 plus R3 IS3. You can always write the solution for any voltage in a very complicated circuit as a linear superposition of all these independent sources with some multiplicative constant. That is a key message that you have to take home in the method of linearity and superposition. Okay, this is the key result. And it can be proven, and I suppose it has been proven to you, and we're going to use this result to do more things, to find Thevenin and Norton equivalent. say we have a very complicated circuit, as has been shown in the textbook, that we have a resistive network. And the resistive network is very complicated. And how do we model this resistive network? We can think of the resistive network as being connected to a current source I, and then we ask what kind of voltage will be developing across this resistive network. Okay? So that is the kind of thing that we can ask ourselves. And then what kind of Norton or Thevenin equivalence can be found from this resistive network? So if we were first to do without the connection of the current source from the outside, if we were to just ask ourselves, how does V look like? Okay, V has to be something of this form. It depends on how many independent current sources and voltage sources you have inside. So V could be something of, say, K1 Vs1 plus K2 Vs2 plus something like R1 Is1 plus R2 Is2. That is just hypothetical. Okay. Now I add one more current source to it. And this current source is called I, an external current source. Then the V in this picture should be just modified by maybe R new, okay, a new current source that I have added times I that is just newly added. Okay, so this is the new term that I just to add to this equation in order for it to satisfy the principle of linearity and superposition. Are there any questions so far? Because I add an external current source, I just add one extra term due to this principle over here. Okay? So because of that, I can think of the first term here as some kind of a total kind of V. It can be called V Norton or V open circuit plus RNI. It can be thought of as something like this. Okay? This whole term over here can be thought of as something like V open circuit. So if I equal to 0, V is V open circuit. And this V open circuit is also often called V Norton. Okay, V Norton. Or it can be called V Thevenin. Let me use the term V Thevenin. Okay, V Thevenin. Okay, so how do we find R sub n? Okay, R sub n can be thought of as the value that is there when I have, say, what I can do now is actually to replace this with the voltage source, where this is V Thevenin, which is the open circuit voltage value of the thing plus a value over here. Okay, and this resistor is always called R Norton, R Thevenin. Okay, R Thevenin, and that the V over here should try to replicate this V that I see here. Okay, you can see that in this circuit over here, if I do add a current to this thing, if I add external current to this thing, I will have a current flowing this way, IRT, okay, which is this voltage drop, is equal to V Norton or V Thevenin plus V. I will have this relationship over here, and from this Kirchhoff voltage law, I get this relationship that V Thevenin must be this current source that I hook onto the outside times RT plus the voltage drop across here. Okay, and this says that V must be equal to VT minus IRT, and hence the Rn over here can be thought of as something like minus RT. Okay? So you can find RT and V by doing two experiments. One is to open circuit the thing and look for what the open circuit voltage is. Then you will only have the first term. And then to find RT, or to find a short circuit current, you just short circuit the thing. And when you do short circuit the thing, then the short circuit current should be equal to V open circuit divided by RT should be equal to V Thevenin divided by RT. Okay. Because of that, I can also transform this source to a, this is called a Thevenin equivalent, the other one will be called a Norton equivalent, as we have seen before in source transformation. Okay, this is still the same resistor as this Thevenin equivalent, and then I will have a current here that is called I Norton. Okay, I Norton should be the I short circuit, because if I were to short circuit this one, the current that flows must be IN. Okay, IN must be I short circuit, and I short circuit is VT over RT. Okay, so that's how you find the Thevenin and the Norton equivalents of an arbitrary resistive network. An arbitrary resistive network, when you look at external source, can always be written in this manner. And when it's written in this manner, it is very reminiscent of what the Thevenin equivalent is. Okay, and hence you try to force it into something that looks like a Thevenin equivalent, and this is what it looks like. Okay, because it has a Thevenin equivalent, then you can also find by source transformation into a Norton equivalent. Okay, the Norton equivalent. And the way to remember that is that this is a series connection, S is closer to T, and this must be Thevenin. This is a parallel connection, P is closer to N, and this must be the Norton equivalent. Okay? Are there any questions so far? Okay, let's see how we apply this in practice to an arbitrary circuit. So if you have a very complicated resistive network, as have been shown in the examples in the textbook, how can we find the Norton equivalent or Thevenin equivalent of this rather complicated looking network? One M, and then I have 4 ohm over here. And I have this plus or minus V out here. And I know that V must be something of this form. If I call this IS, this is VS. Must be something of the form of maybe KIS, maybe KVS plus RIS. Must be something of this form. From the linear superposition principle, yes?
What's the resistance of
There is a resistor up here of 2 ohms. Okay? Thank you for alerting me to that. So we know that by the principle of linear superposition that V has to be something of this form. But we can cast V into something that looks like this, and when it is hooked to an external current source. So we try to find the R's of T in a number of ways. And R's of T we can find by doing a number of things, but we can also find the open circuit voltage first. To find the open circuit voltage, we solve this problem. Okay, we can solve this problem. And let me see how we can solve this problem. And it's been solved in the textbook as well. This is figure 215A. Okay, actually this is actually figure 215A that refers to a previous example in the textbook. And in order to solve that, we let okay, we can see V, that V is equal to Vs divided by 2. Okay? That is, if we switch off this current source, if we just look at having this voltage source being present, if we switch off this current source, I is 0 over here. And what we have is actually a circuit that looks like this. 2 volt, Vs is equal to 2 volt, and then there's a 4 ohm resistor over here, another 4 ohm resistor over here. This 4 ohms, in parallel with this 4 ohms, give us how many ohms? 2 ohms, right? And then there's another 2 ohms resistors over here. So first, if we parallel connect these 4 ohm resistors, we get 2 ohms, and then we parallel connect that 2 ohm resistors, or series connect that 2 ohm resistor with this resistor, then we have 4 ohms, and then the total voltage that we see over here, which is this voltage, is equal to Vs over 2. Okay, because this is a voltage divider. And this can be reduced to something that looks like this. 2 volts with the 2 ohm resistors right on top of it, and then another 2 ohm resistors right on top of it. So this is 2 ohms, this is 2 ohms, and this is V. Can everybody see that V is in fact Vs over 2? Okay, after doing this parallel connection. And then you now turn off this voltage source and look for what the current should be. Okay? And then if you turn off this voltage source, what do we do with it? Do we replace it with an open circuit or a short circuit? Short circuit. Okay, this you replace with an open circuit, this you replace with a short circuit. So if you look at this circuit now, then there was 4 ohm parallel with 4 ohm give you 2 ohms, 2 ohm parallel with 2 ohms give you 1 ohm. Okay? So this 1 ampere is going through 1 ohm. So that 1 ohm is going to develop 1 volt. So if I were to add the contribution from Is, it will be Is times 1 ohm. Because this together with this give me 2 ohms, but the 2 ohms, because this is a short circuit now, this together with this give me 1 ohm. So this is a total voltage by the method of linear superposition. Okay? Is this clear to everybody? So now we ask ourselves, what is V? V is Vs is equal to 2, Is is equal to 1, so V is equal to 1 plus 1 is equal to 2 volts. Okay, this V is my V open circuit. It's also V Thevenin. Okay, that is, so I can figure out what the V Thevenin of this circuit is and what the open circuit voltage is. Okay, then I need also to figure out what the I Norton is. I Norton I find by short circuiting the output of this circuit. Let me short circuit the terminal point of interest to me. So now I'm going to put a short circuit over here. Okay, ask myself what this is I short circuit is, and this I short circuit will be I Norton that I'm after. So let's put the short circuit over there, and let's see what we have. I Norton, well, we will have that 1 amp, this 1 amp flowing into here, okay, would be equal to 0 minus 2, let me see, divided by 2 ohms plus I. Okay, if this is been short circuited, what is the voltage across this 4 ohm resistor? 0 volt, right? Would any current flow through that 4 ohm resistor? Nothing. Okay? So if this is grounded, this will also be 0 volt in this example. Okay? There will be no current flowing through this resistor. By the same token, this has also been short circuited, 0 volt drop across it, no current flows. But the only current that flows is through this resistor. This is at 0 volt, this is at 2 volts. Okay, so this current that flows out there will be 2 over 2, right? In that direction upward. That is the current that flows over there. So that is the only current, and this current that comes here will flow here, and it will add up to that current, and that current is nowhere to go, but becoming the I short circuited or I Norton, and I Norton must be 1 amp plus this current that flows up there, which is 2 volts divided by 2 ohms. Okay, 2 volts divided by 2 ohms. So it's 2 amps altogether. Okay, so I figure out what I Norton is, or the short circuit current is, and then how do I figure out what RT should be? RT is just given by, if you look at these circuits again, okay, RT is given by, if you open circuit this one, okay, IN times RT must be V, open circuit must be V Thevenin. Okay, you can also derive a similar relationship using this diagram over here. Okay, this is V Thevenin. If you were to short circuit that one, okay, you will find that I short circuit should be I Norton, should be VT over RT. Okay, so you can figure out that RT, from both cases, from both equations, RT is just equal to V Thevenin divided by I Norton. Okay, from both equivalent circuit, that should be what RT should be. So we figure out what V Thevenin was. V Thevenin, we found that to be 2 volts, right? There was a V Thevenin. And then I Norton is 2 amps, so RT is 1. Okay, RT is 1 for this picture over here. This is my V Thevenin as well. Okay, so this is a very, maybe not simple example, an example of a complex resistive network that you can find is short circuit current and open circuit voltage, and then from them you deduce the Thevenin and Norton equivalents quite easily. Are there any questions so far? You can also do the long-winded way. You can also combine these circuits, compare the parallel network, and then reduce this to a, by source transformation, to a current source. Okay, current source and then a voltage source, and then combine them and you'll get the same answer. But that's a long way. The short way is actually just to short the terminal over there and open circuit the terminal over there. Okay. There is another way of finding R Thevenin. Okay, there's another way of finding R Thevenin. Another way of finding R Thevenin is to actually turn off all the sources you have in the circuit. And if you do that, then the equivalent, this is R Thevenin alternative, alternate method. In this method, you will turn off all the sources, and if you turn off the current source, what do you replace this with? An open circuit. So if I were to turn off the sources, my diagram will look something like this. And then I will have the voltage. What do I replace it with? A short circuit. So I replace it with a short circuit over there. And then my diagram will look something like this, with all the sources turned off. Okay, this is called the source suppression method. Source suppression method. Okay, and if I put in my 4 ohms over here, and then my 2 ohms over here, and then my 4 ohms over there, and if I look in this direction, if I look with my eyes in that direction, what resistor do I see? I see a 4 ohms in parallel with 2 ohms, in parallel with 4 ohms. So 4 ohms together with 4 ohms give me 2 ohms, 2 ohms together with 2 ohms give me RT equals 1. So it's like this picture over here. If I were to turn off the source and look this way, I just see only RT. Okay? And similar to this picture, if I were to turn off this current and look this way, I see only RT. And that RT has to be this RT. And this RT is this parallel with that, giving 2 ohms. 2 ohms parallel with that gives me 1 ohm. Okay, is this clear? The source suppression method. Okay? Okay, these are kind of very interesting examples because there are no dependent sources in these examples that we have illustrated here. What happens if we have dependent sources? These sources which are independent sources, we have an alternative way, which is to combine all these sources into the simplest. And if we combine them together, we will arrive at something like this or like that. Just using parallel and series connection, source transformation, we can do that. But that method cannot be applied when we have dependent sources. So let's do an example with dependent sources and see what happens. Okay, this is actually from figure 218a. Okay, so the picture looks something like this. 2 amp, and then there's a dependent voltage source over here, which is 2Ix. 2 ohms. It's grounded over here. And then we ask ourselves what V Thevenin should be if this is 1 ohm, this is Ix. Okay? So to find V Thevenin, we let this be open circuit and ask ourselves what that voltage is. So we just go through solving this problem, assuming that we have an open circuit over here. Okay, there's no way we can use parallel connection and reduce this because this is a dependent source. It cannot go away. So to find Vt, first I notice that Ix is equal to Vt minus 2Ix over 1. The voltage here would be Vt minus 2Ix. Because this thing is Ix, this is Vt. Vt minus 2Ix will give me the voltage at this node. And that voltage divided by the 1 ohm resistor gives me Ix. Okay, so that is the first thing that we have. But we also have Vt divided by 2 plus Ix must be equal to 2. Let me explain to you why. Vt divided by 2 is the current going through this 2 ohm resistor. Okay? Ix is going here. Okay? And the current going through this resistor is also the current that goes through this source. And that current is also that thing. So all this current that flow like this is Vt over 2. Okay, that current that flow like this. This current is equal to that current is equal to that current, and that current is Vt over 2. Plus Ix, which is the current flowing down this branch, must be the current flowing into that node. This is just Kirchhoff current law at this node. Okay, Vt over 2 plus Ix equals 2. That's the current that flows there is equal to that. Okay, so we have two equations and two unknowns. From this equation you can solve. You have something like 3Ix is equal to Vt. Okay, and if you solve this equation you will get, I won't solve it in detail for you, but Vt is 1.2 over 5, which is 2.4 volts. Okay. So you find Vt very simply. And how do I find I Norton? This is V Thevenin. I Norton, I will have to short circuit it. If I now add a short circuit, okay, through this, I will get I Norton. Okay, how do I find I Norton? So in that case, then there will be no voltage drop across this resistor now, because this has been short circuited. So there will be no current flowing through that 2 ohm resistor. So I would have Vt is equal to 0 in this example, or V equal to 0. Okay, this voltage will be equal to 0. This Vt, which I call V now, after you short circuit it, that becomes 0. And then this voltage here also becomes 0. Okay, because I short circuit this part now, that voltage there is just voltage over here. It has been short circuit, so this becomes 0. So I would have this equation becoming Ix is equal to 0 minus 2Ix over 1. Okay, this equation is contradictory. So it will say 3Ix is equal to 0. You see the Ix must be equal to 0 for this problem. Okay, so Ix will not flow. So no current flows through this branch. Neither do I have any current flowing to this branch, because this is 0 volt. So I will have 2 amp. And that 2 amp must be flowing like this with nothing going down here, completely becoming In. Okay? And this is my I short circuit. Okay? So the short circuit current can be found very easily. And then R Thevenin would be just V Thevenin divided by In, which in this case is 2.4 volts divided by 2, which is 1.2 ohms. Okay, are there any questions so far regarding how we find RT, VT, and IN? Yes, you have a question.
Could you explain again how Vt is equal to 0 and Ix is equal to minus 2 over?
Well, here in the second experiment that I have to do, I have to short circuit this terminal and look for the short circuit current. Okay, the short circuit current is my I Norton. Okay, so when I short circuit it, this voltage is 0. So V becomes 0. V in the previous diagram, which I call Vt, which was the open circuit voltage, this becomes V now. Okay, I can draw another diagram, but I just want to use back the same diagram. A little bit confusing, but now this is also called V. Okay, this becomes V. Okay, it's not, I shouldn't call it Vt in the second example over there. Okay, and that becomes 0, and that equation there is just this one. This implies that no current can flow down here. Okay, and then that is what I get. So I find my RT using a very simple method. And in the previous example that I had, I have two ways of finding RT. I find RT after I found VT and IN. Okay. Another example, another method was a source suppression method. I turned off all the sources and looked in this direction and asked myself, what resistor do I see? There's another way of finding RT. But you can also apply the same technique as you had over here to find RT, but you have to do something. Okay, you have to do something that's slightly different. Say if I turn off all the sources I have in this circuit, ask myself, what circuit do I see now? If I turn off my sources, the current source becomes an open circuit, as all of you know. Okay? Then the circuit that I have after source suppression is that it looks something like this. Okay, I can not simplify this circuit any further because this is a current dependent source and this is Ix. And I ask myself, how can I figure out what this resistor is since there's a dependent source in there? Okay, in order to figure out what the resistance is like looking this way, I have to send in a test signal. The way to send in the test signal is to hook this to a current source. I can assume that the current source is 1 amp. Okay? And ask myself, what voltage develops across that terminal? And using this relationship, I can find out what the resistance is looking that way. Okay, this is called the test signal method. You need to do that because otherwise there will be no activity in this thing. Otherwise, if Ix is equal to 0, this voltage drop is equal to 0, and nothing happens in the circuit. Okay, so you have to probe it with a signal.